Okay, let's get started. This is the second part of the core science chemistry revision. So starting off then, we're going to look at metals. And the main bit about this topic that we need to know about metals is the group of metals in the middle of the periodic table here, which are called the transition metals. And don't forget, you'll get this periodic table on a data sheet when you actually do your exam. So these transition metals in the middle of the periodic table have several properties that we need to know about. First of all, they are good conductors of heat and electricity. So if you remember from the P1 topic, they're good conductors because they've got those free electrons that allow to flow through the metal, and also good conductors of electricity, which you'll remember perhaps by having a look at copper here and remembering that copper is used in electrical wiring. So further to that, they are also strong, but they can be bent or hammered into shape, which is really important because it makes them really useful for use as pipes and things like that. You might also see the words malleable in association with the fact that they can be bent easily, and also the word ductile. They may use that in your exam, and that means it can be drawn into wires easily, hence copper wiring and the use for that in electricity. Now, further to this discussion of the properties of the transition metals, there are also a couple of metals that we need to focus on, and they are titanium, which you find here, and aluminium, which you find over here. So titanium is a useful metal and can be used for things like hip joints, which is shown in this picture above here, and aluminium can be used for aircraft. Okay, so it can be easily shaped and turned into an aircraft body. A few properties that make these really useful: they both are low density, which makes them quite light metals, and they are resistant to corrosion. So both aluminium and titanium have these properties. Let's face it, if you put a hip joint in your body, you don't want it to corrode, okay? You don't want it to break down and rust, otherwise that will cause loads of problems. Also, you don't want it to be too heavy. So a low density corrosion resistant metal would be excellent for a hip joint. Secondly, for aircrafts, again, you wouldn't want that to corrode and react with the rain and make rust and things like that. And also, being an aircraft, it has to be quite light and therefore have a low density. Hip joints are also very strong because titanium metal is particularly strong. Aluminium is not very strong, but it can be made into what we call an alloy that are strong, okay? But it can make strong alloys, and we'll come across what alloys means in just a second. Okay, so that's just a quick summary of some of the properties of metals. So you might get a question on the properties, and it will focus on the transition metals and the hip joints. For a question in the exam, they might talk about a specific object and made out of a specific metal, and they might ask you, for example, what properties make this a suitable metal. And you need to think about if it's a transition metal, things such as this, or specifically density and corrosion resistant for titanium and aluminium. Moving on then, we're going to talk about alloys. And this is a really common question that they like to ask in an exam. So we're going to look at the difference now between a pure metal and an alloy. A pure metal, if we were to draw its atoms, they would have a regular arrangement. But this regular arrangement actually makes them easy to slide over each other because of these layers in these, all the atoms are the same size, they are layered up and they can easily slide. That makes a pure metal quite soft. On the other hand, an alloy is a mixture containing at least one metal. Now that might be a mixture of metals, or it might be a mixture of a metal and a non-metal. For example, steel, which we'll talk about in a minute, is a mixture of iron, a metal, and carbon, a non-metal. And we would draw an alloy slightly differently. So rather than this regular arrangement of atoms here, because they have two different size atoms now, let's for example take iron and carbon, you might have iron atoms here, and you would have carbon atoms in between those, and there would be a different size. And because they have different size atoms in an alloy, it stops them having this regular arrangement. So they've got different sized atoms, or different sized particles, you can say, if you can't remember the word atoms, and this distorts the regular shape. It's no longer regular. Now you should try and make yours still touching as much as possible, because obviously it's still a solid, but you get the idea that we no longer have these regular lines. So it distorts the regular pattern, and they can't slide over each other. So a really common question for perhaps you to be able to draw a similar structure to this, or at least explain why an alloy is stronger than a pure metal. So over here, we're going to focus on a particular alloy, iron and carbon. And there's different versions of this alloy that we can make. So different versions of this steel. We can have low carbon steel, and that would be a steel with just a little bit of carbon in it, so around 0.1%. So because it's got a little bit of carbon in it, imagine just putting a little bit in between here, it would distort the layers and become an alloy, but it means it can still be quite easily shaped and bent, like the pure metal. And in that case, it can be used in things like car bodies, like this one shown here. The second one we're going to talk about is high carbon. So that's adding a little bit more carbon, distorting those layers even more, making it that bit stronger. And high carbon is hard and not flexible. And it's used in things like building bridges and also blades on cutting tools as well. So if you increase the amount of that second sized atom in there, you're going to make a stronger alloy. And the final one then is stainless steel, which I'm sure everyone's heard of. And the benefits of stainless steel are that it's resistant to corrosion, so corrosion resistant. So that's important for things like cutlery, because you don't want the things that you're eating with reacting and corroding before you put them into your mouth, otherwise they'll make you really poorly. Okay, so things like cutlery, and also containers for corrosive materials, you can make out of stainless steel. And stainless steel is a little bit different. So as well as the carbon in there, it will also have bits of other metals, sorry about that, like chromium and maybe nickel. So that stainless steel has an alloy of different metals in as well. So that is your summary of metals and alloys. Moving on then, I'm going to talk about fractional distillation, and this is a really big topic, and we're going to go all the way from crude oil, that fossil fuel that you get out of the ground, all the way to plastics. So if we're moving from crude oil to plastics, we're going to start off with the idea that at the bottom of the ocean, you would drill down and you would find a well of crude oil in the bottom, and you would extract that oil. And you would take it back to the shore on a rig, and you would take it to somewhere like this, which is a fractional distillation tower. The fractional distillation tower then is where crude oil is separated, and you have a mixture of hydrocarbons in that crude oil. And what hydrocarbons are molecules with hydrogen and carbon. But the trouble is crude oil is a mixture of these hydrocarbons, so it might have some short chain hydrocarbons, so really small ones. There's your carbon and your hydrogen in that molecule. And it might have also some really long chains containing carbon and hydrogen. And we call these hydrocarbons, these molecules here. Clues in the name there, you've got hydro for hydrogen and carbon for carbon. Now, when it's a mixture like this of all different lengths, I'm just going to draw them as little squiggles here, it's a little bit useless. What you need is for it to be separated into its separate lengths, and that's what this fractional distillation tower is for. You can see down the side you've got things like petroleum gas, petrol and diesel coming out of the fractional distillation tower. Now, importantly, you don't need to know the names of these that come off the side and where they come off. You just need to have an appreciation that most of these are fuels, and most of the crude oil, once we've separated it, is useful for fuels. But we're going to talk about how it goes on to make plastics a little bit later. So into the fractional distillation tower goes different lengths of hydrocarbons. So you'd have short ones and long ones as a mixture going in, and it is heated. Now, the whole point that this can be separated is because these different lengths here have different boiling points. And the boiling points of these molecules increase with size. So this one, for example, would have a low boiling point, and it would increase with its size, whereby long chain molecules have a really high boiling point. So boiling point, remember, is just the temperature at which it boils. So the temperature at which it turns from a liquid to a gas. So as they go in as liquid, they will then be heated and they will start to rise up the fractional distillation tower. Now at the bottom it's really hot, it's around 600 degrees C, and at the top it's cooler, around 20 degrees C. So straight away, if the small hydrocarbons go in, because they've got a low boiling point, let's say for example one of them goes in with a boiling point of 40 degrees C, that will turn into a gas straight away and start rising up the fractional distillation tower. So the first step that we've got is evaporation. Short chain molecules evaporate because they've got a low boiling point. They're going to turn from a liquid into a gas and start rising up the tower. Now, importantly, when they come off the tower, off of these sides up here, they are a liquid. So they start off down here as a liquid, they turn into a gas, and then they are collected again as a liquid. Because at these points in the tower here, we have the molecules condensing. So first of all, we get evaporation, and then you've got condensation to collect those fractions off of the side of the fractional distillation tower. So what we need to remember then is the process that we got, evaporation and condensation. One really important thing to remember is that boiling point is the same as condensing point. That's to say that the temperature at which it turns from a liquid to a gas is also the temperature at which it turns from a gas to a liquid, depending on whether it's being heated or cooled. So here it's being heated, so the molecules are going to turn from a liquid to a gas. And where we started here with the molecule at 40 degrees C, when it's heated, it will reach 40 degrees C and then will be collected off as a liquid, where it turns back into a liquid again. So the key point for fractional distillation tower then is that these molecules are separated by their boiling points, and that they evaporate and then they condense and are collected off the tower. Now, up the top of the tower, this is where you get your short chain hydrocarbons, and the short chain hydrocarbons are very volatile. That means they turn into a gas easily. You can see here petrol is quite near the top of the tower, and if you go to a petrol station you'll smell the petrol because you'll smell that liquid turning into a gas really easily. Because they are volatile, they are also particularly flammable, so they ignite easily, and the ones at the top are the ones with the low boiling point. Contrastingly then, down at the bottom, you've got your long chain molecules, and they have a high boiling point. So even though this is heated up to a great temperature down here, the bitumen that comes off, which is used for roads, won't actually boil. That'll come off at a liquid, because these are like chains with about 70 carbons in them, really long chains, and they don't reach their boiling point. We call these ones at the bottom as well really viscous, which means that they're really thick and they don't flow easily, whereas the ones at the top flow really easily. And opposite to those, they're not very volatile and they are not very flammable. So that's a summary of the fractional distillation tower and how that works. You need to remember the idea that these particles are evaporating, and then when they reach their condensing point, they will condense into a liquid and be collected off the side. And most of them are really useful fuels. Okay, let's talk now about environmental problems that are associated with burning these fuels that come out of the fractional distillation tower. So we said things like petrol and diesel come out of the tower, and these consist of hydrocarbons. So I'm just going to use a really short hydrocarbon of methane to help us. So methane, if we were to burn methane, you need to remember that the gas you're reacting with when you're burning is oxygen. So you need air for the combustion process to happen, which is burning, and it will react with oxygen. This comes up quite a lot in the exam, so you need to remember this. And when we're burning, this process is called combustion, and this will be a name for a reaction that you'll have to remember. So whenever you combust something, you react it with oxygen, and you always make carbon dioxide and water. Now let's have a look at how we can predict what we've made here, because if we look at this, we can have the C, which you're reacting with the oxygen to make carbon dioxide, and you've got the H, the hydrogen, which you're reacting with oxygen to make water, or H2O. So these are the products that are made from combustion. Remembering in equations, everything on the right hand side is products, and everything on this side is reactants. And we would need to balance this equation. So for higher T, you might be asked to balance equations. So because we've got 4 hydrogens over here, we'd need to double that, and that would give us 4 hydrogens, but on this side in total, it would give us 2, 3, 4 oxygens, so we'd also need to balance it there. And now our equation is balanced. So the environmental problems then associated with burning these fuels. Now the first one is obvious from this product, this CO2 here. This comes up so much in the chemistry exam. The problem is that carbon dioxide is released, and this causes global warming. If there's one thing that you need to remember for your exam, it is this, because this is bound to come up somewhere. The second problem is, if there are impurities in the fuel, some of the fuel contain something called sulfur. And if we burn the fuel containing sulfur, we create sulfur dioxide, because you can see the sulfur would react with the oxygen to make sulfur dioxide. The final thing is that it can make solid particulates, and this can cause global dimming. Okay, so the sulfur dioxide, I forgot to say, this can cause acid rain, because when this gas goes up and dissolves in the rain, sulfur dioxide causes acid rain. Now rain is already slightly acidic, but when the sulfur dioxide dissolves in the rain, it makes it more acidic. Okay, so 3 environmental problems associated with burning fuels that we need to remember. Carbon dioxide causes global warming, sulfur dioxide causes acid rain, and solid particulates, that means solid bits coming out, for example, of the car exhaust, that would cause global dimming. We don't see it very much in this country, but we do see it in countries such as China. We get lots of smog. Now, to prevent sulfur dioxide coming out of things like power stations, they have scrubbers inside, which are chemical scrubbers to remove the sulfur dioxide before these gases are released. And actually, most of what's released from a power station, it looks like a load of smoke and fog, but a lot of it is actually water vapour. But obviously, we've got the CO2 going out there as well. So in these power stations, these scrubbers remove the SO2, or the sulfur dioxide. Okay, we've looked at the fuels from crude oil and their use in power stations and cars and the environmental problems they can solve. But a really hot topic is the use of alternative fuels, because we're trying to avoid using crude oil because that's a non-renewable resource. So we're trying to think about some other fuels that we can use, and these ones are ethanol, biodiesel, and hydrogen. Now, starting off by looking at ethanol then, we're going to discuss ethanol in a little bit more detail later on, but ethanol is a type of what we call a biofuel. And it can be made from crude oil, and we'll discuss that later, but we're going to talk about it in terms of a biofuel here. Biodiesel is also a biofuel. And bio, like biology, the study of living things, biofuels are made out of living things, aka plants in this case. So with ethanol, when you burn ethanol, again, you'll be reacting with an oxygen in a combustion reaction. But this time, the carbon dioxide that you produce, we will class as carbon neutral. And that'll be the same for the biodiesel as well. So that's really important. And I'll just explain what that means there, because both of these involve plants and the fuels that are made because are made from plants. We call it carbon neutral because even though they are going to release carbon dioxide, so when ethanol reacts with oxygen, it will produce that carbon dioxide and water. But importantly, the carbon dioxide released won't give out an overall increase in carbon dioxide from the atmosphere. Because they're made from plants, as the plants are growing, they will take in carbon dioxide through photosynthesis. And when they are then burnt, they will release that CO2 when they're a biofuel, but it's only releasing the CO2 that it's taken in. That's why we call it carbon neutral, because it's taken CO2 in whilst it's growing. So then when we burn it, we are releasing that CO2 again. It's not CO2 that's locked up in fossil fuels. Okay, so this idea we call carbon neutral, which means there's no net or no overall increase in the carbon dioxide released. So no net CO2 released. So ethanol is made from a process called fermentation, which I'll discuss a bit later, and it uses a sugar plant, which is a big sugarcane plant, and it is broken down, and that sugar in that plant is broken down into carbon dioxide and ethanol. So this uses a plant, and therefore it's a biofuel. In the same way, biodiesel is a biofuel, and this is made from vegetable oils. Again, carbon neutral, because the vegetable plants would have taken in carbon dioxide, and then when you burn the fuel, it's only releasing the carbon dioxide it's taking in. And this can be mixed with regular diesel, which makes the fuel slightly more environmentally friendly overall. With the biofuel as well, because there's less impurities in it than the regular diesel, there'll also be less of that sulfur dioxide released as well, and that'll mean less acid rain. The trouble with the ethanol up here is you have to have an engine that is designed to specifically take in that ethanol, because it's slightly different burning ethanol to burning regular fuel. The biodiesel, again, you might need an adapted engine. I mean, it can be mixed in with a diesel, but that can add prices up as well if you need to adapt the car engine in any way. With hydrogen then, this is really important because this is where the technology is going at the moment. Now, if you think about it, again, if you burn the hydrogen, you have to react it with oxygen. But if you have a look at this equation, hydrogen and oxygen, have a think to yourself, what's the only thing that you can make if you react these two things together? Okay, that is going to be water. So hydrogen and oxygen make water. We can just balance that equation out because I'm sure some of you will be looking at thinking it's not balanced. So we need 2 of those and 2 of those to balance it out. And this is really important because it only makes water. You are not making this carbon dioxide that you did before. So no CO2 released, which is obviously really important because that means it doesn't contribute to global warming. So if we could run everything off of hydrogen, that would be fantastic because we'd be only adding water vapor to the environment and no CO2. But the problem with this is that the engines are really expensive because you have to adapt them to use hydrogen. And secondly, it's really difficult to store because it's so explosive. Hydrogen, that's the gas that's used in hydrogen bombs as well. It's really difficult to store. So just going from that idea of you moving from crude oil to alternative fuels, and just bear in mind that idea of a biofuel made out of plants or living things. And this idea here is really important with hydrogen only producing water. Now, for all of these reactions with fuels, don't forget that they are combustion reactions, and that you are always reacting with them with oxygen each time. So here are a few questions for you to answer, and I'll come back and see if you got them correct. Okay, let's check your answer to these questions. Which problem is caused by solid particulates? That is global dimming. Again, not a big problem in this country, but it is in other larger industrial countries across the world. Why is burning hydrogen better for the environment than burning a fossil fuel? That's because the only product is H2O, or water. And that means there's no CO2. And that means there's no contribution to global warming. Question 3, what does carbon neutral mean? Carbon neutral means that there is no net CO2 released when a biofuel is burnt or when a fuel is burnt, but it'll only be carbon neutral if it's a biofuel. Question 4, an example of carbon neutral fuel, you could have had ethanol or biodiesel. Which gas causes acid rain? That is SO2 or sulfur dioxide. Where do viscous molecules leave the fractional distillation tower? That's at the bottom. Number 7, a hydrocarbon has a boiling point of 50 degrees C. What is its condensing point? Now, if you remember, boiling point equals condensing point, and I've seen this so many times for 1 mark on a test. So bear this one in mind, that your boiling point is the same as your condensing point. If it's 1 mark, they're not asking you to do a lot of working out. It's just that it's the same value, 50 degrees C. Okay, moving on then to a specific hydrocarbon called an alkane. So if you remember before, hydrocarbons are molecules that contain hydrogen and carbon. Then alkanes are a specific type of hydrocarbons that we are going to look at. And the first one is methane. Now, methane contains 1 carbon. Ethane contains 2 carbons. Propane contains 3. And butane contains 4. And the way I like to remember that is by a little riddle, which is monkeys eat peanut butter. So if you remember monkeys eat peanut butter, you remember the MEPB bit and the idea that it goes up in order of size from 1 carbon to 4 carbons. So as these are hydrocarbons, we've drawn the carbons in, but now we need to draw in the hydrogens. And the thing with alkanes is they are all single bonds between the carbon molecules. So first of all, let's draw these single bonds in here. So just a line represents a bond. And then we've got the hydrogen molecules around. Again, all of the hydrogen molecules are always single bonds anyway. A rule you need to remember is that each carbon can have only 4 bonds. And we'll check and count in a minute to make sure that each carbon has 4 bonds. Don't forget that the H's and the C's all have to be capital letters. You won't get marks if you do them in lowercase letters because they are elements from the periodic table. So these are special hydrocarbon molecules called the alkanes. And we need to remember this rule that each carbon atom has 4 bonds. And it always has to have 4 bonds. And that's really important. And we just count the bonds by looking at how many lines come away from the C. So we can see here that we've got 1, 2, 3, 4 lines coming away from the C. We'll check this C here. We've got 1, 2, 3, 4 lines. This one here, 1, 2, 3, 4 lines. And we do the same with all of them, okay, just to make sure we've followed this rule when we've drawn these hydrocarbons. And because they've only got single bonds, we call these saturated molecules, which means they're full up of hydrogen. You can't fit any more hydrogen around because you can't put any more bonds around the molecule because they are full up. So they're full up of hydrogen, you can't fit any more on there. So these alkanes, we give a general formula, which is CnH2n plus 2. And what this means is that for whatever number of carbons you've got, to find out the number of hydrogens, you would double that and add 2. For example, if we had 6 carbons, for example, to find out the number of hydrogens, you would double 6 and add 2. So that would be 14. Or for another example, if we had 10 carbons, to find out the number of hydrogens, we'd have to double it and add 2. So it would be 22. And these are alkanes. And if you saw a formula like this, you would have to work out whether it's an alkane or not. Now, the final thing is how we write these molecules in their formula. So this we've drawn is their structure, and now we can write them in their formula. So methane here has 1 carbon, so it'd be CH4. Ethane would be C2, H6. Propane would be C3, H8. And butane would be C4, H10. Those are how we write the formulas for methane, ethane, propane, and butane. Monkeys eat peanut butter. So for the alkanes, we need to remember they're saturated. We need to remember they got single bonds. We need to remember this rule. And these are the ones that come out of the fractional distillation tower. Obviously, you're going to get loads more right down the bottom of the tower that have like 60 carbons long. And they are really useful fuels. Moving on then, we are going to go from the alkanes to alkenes, and this process involves cracking. So we're going to take some alkanes, and hopefully at the end of this process we are going to end up with a different molecule called an alkene, which only differs by that letter there. It's either an alkane or an alkene. And this process involves cracking. So what you do is you take your alkane, so you might have some mineral wool here with your long chain alkane on. We'd have a long chain. And we might want to crack that to make an alkene. So for example, when we had the fractional distillation tower last time, I said you don't need to remember where things come out, but in a question they might tell you that diesel comes out lower than petrol on the fractional distillation tower. This means diesel chains are longer and petrol chains are shorter. So if you wanted to make petrol, you could take a long chain diesel molecule, crack it somewhere, and make some petrol. And then you'd end up with another product as well. And this all is important in relation to the supply and demand for fuels. And they really like these questions on supply and demand. For example, if your demand for petrol was high, so the customers wanted petrol, but your supply was low, you might then be able to crack some diesel if this was in high supply. You could crack some diesel and make petrol out of it for your consumers. Okay, so this is the cracking process, taking a long chain alkane and making an alkene. So what happens is you would heat this up and you would allow the vapors to run over a catalyst. You'll see a catalyst in a few reactions in this C1 topic, and they are something that speeds up a reaction without being used up. So they're not actually reacting with the alkane, they're just allowing the reaction to happen faster. So if we heat this up, that will then give us an alkane and an alkene. So the products of cracking will be two shorter molecules. One of those will be an alkane and one of those will be an alkene. So we've got a long chain alkane, and our products are going to be an alkane and an alkene. For example, if we had a long chain alkane that was C8H18, for example, we could crack that and make two smaller molecules. Now we can make another alkane, which may be C4H10, for example. But then we would be left over with just, if we look at these numbers, we'd be left with 4 carbons, so C4, and only 8 hydrogens. Now this molecule here, and we'll discuss why in a minute, is called an alkene, and this molecule is an alkane. This molecule follows that general formula for an alkane, which is CnH2n plus 2, as does this one, this longer chain here, CnH2n plus 2. Our general formula is there. However, this one, as you can see, has a different general formula of just CnH2n, where you've just simply doubled the carbons that you've got. And this is the different type of molecule. This is the alkene, and this is the general formula for an alkene. So this cracking process is really important. It's our next step into moving, like we said before, from that crude oil into our plastics. Because we've talked about how useful alkanes are as fuels, but this time we're going to start moving towards how we make plastics. And that involves these alkene molecules here. So we need to remember the conditions needed for cracking are temperature and a catalyst. And you also will need to recognize that this reaction here, where you're heating something up and breaking it down into two smaller products, is an example of a thermal decomposition reaction. Thermal decomposition means breaking down with heat, just like you would have seen the thermal decomposition reaction in the limestone cycle. So here we're breaking down this long molecule into two smaller ones. You can see it's not reacting with anything. That is a sign that it's a thermal decomposition reaction, because it's simply just breaking down when you heat it up. So we're going to go on to next talk about how these alkenes can be used to make plastics. But this general idea comes up a lot, this cracking idea, the conditions needed for it, and we just need to bear in mind that we're taking a long chain and cracking it into an alkane and an alkene. Okay, moving on to alkenes then. Again, they're differ by just this letter only. Okay, so they're not alkanes this time, they're alkenes. Now before we said alkanes were saturated, but this time alkenes are what we call unsaturated. And that is because between one of their pairs of carbons, they have a double bond. So they would have a double carbon-carbon bond in there, just like this somewhere. And this is why we don't get the molecule methane. Because if you remember, from Monkeys Eat Peanut Butter, things starting with M had 1 carbon, E was 2 carbons, P was 3 carbons, and B was 4 carbons. And it was fine to have methane, but we can't have a double bond if we've only got 1 carbon. So we can't have methane, and that doesn't exist. But we can have ethene, and that will have 2 carbons. So ethene here, we draw with our 2 carbons with a double bond. That's how we start off it. And then we need to remember our rule that each carbon makes 4 bonds. Now the important thing to remember is this double bond counts as 2 bonds because there's 2 lines. So we can only have 2 more bonds with our hydrogens on. For propene, monkeys eat peanut butter, so that's 3 carbons. One of those has got a double bond and only one of them. And this time we need to count and make sure each carbon has 4 bonds. So 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. You can see in these larger molecules why we call it unsaturated, because it's not full up of hydrogens. Because of this double bond, you could fit a hydrogen there normally and a hydrogen there, but because of this double bond here, it means you can't do that, so they are unsaturated. Butene then, monkeys eat peanut butter, so that would have 4 carbons. So we'd start drawing the 4 carbons, and then one of those has a double bond. It doesn't matter where you put it, but I try and make it easier for yourself, put it at the start or the end. Easy to make a mistake when you're drawing these. I'd recommend drawing the carbon bonds in first. That makes it a little bit easier, because here we can only have 1, 2, 3, 4, so we can't have a hydrogen down here. 1, 2, 3, 4, and 1, 2, 3, 4. Okay, just check each time that you've got 4 bonds only around these molecules, because that's really important. And you can see again how it looks to be unsaturated. So anything with a double bond is unsaturated. As we said on the previous slide, the general formula is CnH2n. And if we were to write the formulas for them, ethane would be C2H4, propene would be C3H6, and butene would be C4H8. So you can count again and just make sure you've got 8 hydrogens and 4 carbons if you need to. Now we can test to see whether something is an alkane, like before, the single bonds, or an alkene. And the test that we do to do that is add bromine water. And if it's an alkene, if it has a double bond, the bromine water will turn orange to colourless. It's really important in your exam that you say colourless and not clear, because clear just means that you can see through it. But it's important that we use the word colourless to show that it actually has decolorized. So it actually has gone to a solution that has no colour in it at all. Because the orange could be clear, you could see through it, even if it's orange. So it's important that you say it turns from orange to colourless. And it does this when it recognises that double bond. So there's a number of ways you could talk about this bromine water. You could say it was a test for alkenes. You could say it was a test for unsaturated molecules. And you could say that it was a test for double bonds. Okay, so those are our alkenes. And we're going to talk about next how these alkenes will go on to make our plastics. So here are some questions for you to answer, and then we'll come back to talk about polymers and plastics. It says, which molecules are saturated? Those are the alkanes. Which type of reaction is cracking? Hydration or thermal decomposition? It is a thermal decomposition reaction. draw butene. So the first thing we need to think about is, has it got single bonds or a double bond in there? It's an alkene, so it's got a double bond. So we'll draw the 4 carbons for butene, remembering monkeys eat peanut butter. 1, 2, 3, 4. So we've got 4 carbons, a double bond in there, and then we need to complete by adding the hydrogens. So 1, 2, 3, 4 bonds. 1, 2, 3, 4. 1, 2, 3, 4, and 1, 2, 3, 4 to give us butene. Is C2H4 saturated or unsaturated? Because it's just got that general formula of CnH2n, that's an alkene, so it'll be unsaturated. And name that molecule. Well, it's got 2 carbons, so it must be ethene. And finally, what would happen if you put bromine water in butane? Well, it doesn't have a double bond because it's an alkane. So sometimes they'll give you a trick question like this. It has no double bond between those carbons. So the bromine water would stay orange. Or you might write, will not decolorize. So I put that there in purpose because they often try and trick you out by giving you an alkane there. So just bear in mind whether you're talking about an alkane or an alkene. So moving on then, we're going to talk about polymers. And this is in our quest to move from crude oil to plastics, as we started out before. And as we've been talking about this, we talked about separating the hydrocarbons in the fractional distillation tower, talked about alkanes, cracking, and alkenes. And the whole point of cracking is that you want to get yourself an alkene like one of these, ethene, propene, and butene. But now we've got these alkenes, we call them monomer units, which just means they're single units, single molecules. And to make a plastic, or we can call these polymers, we want to join these all together again. So you want to join all these monomer units together into one long chain. And that's what a polymer is. If they ask you for a definition, just need to get the idea that it's a long chain of repeating units. And this might be several hundred molecules long. So you want to turn monomer units into a polymer, where poly just means many, and mono means just one. So the conditions that you need for cracking are pressure and a catalyst, again, to speed up that reaction. Now you can kind of think about the conditions needed and try and remember that they're pressure, because here you've got some molecules here that you kind of want to squash and press together to get them all joined in one chain. Whereas the opposite, when we're talking about cracking, you wanted to break that long molecule up, and therefore you'd want heat to break those bonds. So there's a couple of ways to try and remember these conditions, and both of them need a catalyst to speed up the reaction. Now we start with our monomer units, and there's a special way we draw these. We draw them in brackets, and we just draw our ethene molecule. So ethene has 2 carbons, and it has a double bond because it's an alkene. And we draw it in brackets like that. And we just put an N here to show we could have any number of these monomer units. So for example, over here, our N would be 3. So any number of these monomer units can then be joined together under pressure and a catalyst to make a polymer. But rather than writing out this hundreds and hundreds and hundreds of times, we just show what each repeating unit of that polymer would look like. So we show it in brackets again. And what happens is the double bond breaks, which allows the carbon to join onto another molecule. So the polymer unit we would draw without a double bond, and we would put the little n down here in the brackets to show that if we had 10 of these, then our long chain would be 10 of these units long. But the important thing to this is we put the bonds outside the brackets, and this shows that actually this is just one small unit of a very long chain of monomers all stuck together. So don't forget, the monomers have a double bond in, but when it's turned into a polymer, that bond breaks and you have a single bond. Now, rather than writing longer ones out for propene, they kind of write it in a condensed way. So they would have N, and then they would have the carbons here, and the third carbon will just be down here, compacted up in this little package here. So just bear that in mind. They might ask you to name this monomer unit, and when they do, you just need to have a look and see how many carbons there are in total. You can see there's 1, 2, 3, so it must be propene. And then again, under heat and pressure, this would be put into a polymer unit without a double bond. And you may be asked to draw these, or you may be asked just to name these. So that should be CH3 with the bonds extending through the brackets, and that is your polymer unit for propene. Now, the name that we need to use, well, when they're a monomer, we just use the name that they've got, ethene, propene, or butene, for example. And when they turn into a polymer, well, naming polymers is really easy, because all you need to do is to put the word poly in front of the monomer. So we have polyethene that we've made. We've got polypropene. And if we were to make one out of butene, we'd have polybutene, but it'd be very unlikely in the exam if they talk to you about polybutene. These are the two more likely ones they'll talk to you about in relation to polymers, ethene, propene, making polyethene and polypropene. Now bear in mind that this process has a name called polymerization. So the clue's in the name, it's got the word polymer in there. So this process is making polymers. Okay, so I've got a few questions to ask you about these, just to check your understanding of this polymerization process. Okay, so have a go at these, and I'll come back in just a sec and see if you got them right. So for the first one, it says draw the monomer unit for ethene. So for ethene, we need to think that it's got 2 carbons because monkeys eat peanut butter. So we need to draw 2 carbons with our double bond. It's asked for the monomer unit. So we need the double bond intact, and we need to add our hydrogens. And then we need to put our N over here. Now for the polymer unit of polyethene, we need to break that double bond and have our bonds extending through the brackets and our N over here. The last question, a polymer was made from a monomer called styrene. What would the polymer be called? Well, you simply just add the word poly in front to make polystyrene. So very well done if you got those correct. And that kind of completes how you get from crude oil to plastics. And this is a massive topic, and people don't realise that actually all the plastic things that they're using every day are actually made from this fossil fuel crude oil. And we've talked about a few processes involved. We talked about fractional distillation and separating that mixture of hydrocarbons by their boiling points. We then talked about cracking, when you take a long chain hydrocarbon and split it, and that's where you get your alkenes from. And then we talked about polymerization. So a massive number of processes to go through to turn crude oil into plastics. And just remember that alkanes are useful fuels, and it's the alkenes that go on to make the plastics or the polymers. Okay, so that's fractional distillation. We're going to go on to now to talk in a little bit more detail about ethanol. So we briefly came across ethanol earlier when we were talking about biofuels. And when we're talking about biofuels, we're talking about this method here, fermentation, whereby you use a sugar plant, a sugarcane plant, and with yeast, yeast will help break down the sugar into carbon dioxide and ethanol. And then that ethanol is a really important fuel, and you can use it in cars, for example. We're designing these new ethanol cars, but those engines are quite expensive to adapt to use that ethanol fuel. But that's one way to make it. This way is called a biofuel because it's made out of a plant, made out of a living thing. Now, some advantages to that, the fact that it's made out of a renewable resource, and that it's carbon neutral, which means there's no net release of carbon, as we discussed earlier. But some disadvantages are that it's a slow process. Obviously, it takes time to grow all of this sugarcane, and it takes time for that yeast to break down the sugar into carbon dioxide and ethanol. And also, it's a batch process as well, which means it's kind of stop-start process. And after we've created this ethanol, because it might have this plant material in and things like that, it will also have to be purified, and they do that by a distillation process. And we'll come across distillation in just a little while as well. Another disadvantage is that this land that's being used for fuel is not therefore available to be used for food. So it drives up the food prices because the land is being used to make plants for fuel. Okay, now this contrasts then with the second process I want to talk about is hydration with ethene. Now, if you remember hydration reaction, just like you hydrate yourself when you drink, you're adding water. So you would get ethene, add it to water, and make ethanol. And this process, again, like most of them in this topic, requires a catalyst. And this obviously is from crude oil. So the origin of this is from crude oil. Obviously, we take a long chain hydrocarbon, crack it to get this alkene, this ethene. But the first resource of it was crude oil. So it's a non-renewable resource, which is contrasting to this one, which is renewable, because it's made from that crude oil. So that's its main disadvantage. It does have a few advantages though, and it's a fast process, and that it's a continuous process. You don't have to stop and start this. It can just be continuously running all the time, and the ethanol can be collected off. And that makes it quite a cheap process as well. You're not involved with massive harvesting and transporting of all this sugarcane like you would be over here. So bear in mind, this could be a 6-mark question. I've put it up here in the type of framing that they might give. So compare the advantages and disadvantages of making ethanol by fermentation and hydration with ethene. You might have to explain, for example, how each of them works, and also give a summary of advantages and disadvantages of both of those processes. Ethanol then can be used as a really important developing fuel and a biofuel, which is why we make it. So I'm going to move on now to talk about plant oils. And this is a really old picture of a donkey pulling around a heavy piece of concrete to allow plant oils to be extracted from bits of plant. So plants such as olives, for example, have big stores of oil in them. And we would want to use that oil for cooking and for eating, and sometimes for biofuels as well. So sometimes plant oils we might want for food, sometimes we might want to use them for biofuels, like the vegetable oils that would go into biodiesel, for example. And to get these oils out of this plant, first we would have to crush the plant. That's our first process. And then we'd have to press it. And in the pressing process, we'd get these large stones, and sometimes you'd see it in this kind of format where you'd have your plant material squashed and sandwiched between these large stones. And that would then allow the oil to drip out the sides and be collected. So this pressing process, when they add a big bit of weight to the plant material to try and get that oil out. Now, once they've done that, they might have to filter the stuff that comes out, because you imagine this probably has little bits of plant material and things in as well as oil. So they might have to filter it, or they could distill it in this distillation process, which is a bit like fractional distillation. You are heating something up and you separate them because they have different boiling points. So in here, for example, you could have a mixture of oil and water that has come out of the plant that you need to separate. and you would heat it up and you would evaporate the water. That would then cool down and you could collect it off so that you would have your oil in here. So much of this process means that actually you have to purify the oil afterwards. Now, one thing that they do like discussing in C1 is energy, and just bear in mind that this distillation process will require a lot of energy, whereas filtering does not require much energy. But if it's not pure, you might need both processes to try and purify those plant oils. So we need to know a little bit more on plant oils, and especially for the higher tier, there's a couple of things that come into play. Now, first of all, there's two types of plant oils, and this brings up these words again: unsaturated and saturated. So plant oils are long chains which are full of carbon atoms, a bit like those hydrocarbons we saw earlier. And again, they can be unsaturated ones, which means they contain double carbon-carbon bonds, or saturated ones with single carbon-carbon bonds. Now, the unsaturated ones are slightly healthier than the saturated ones, which tend to be more unhealthy. Now, the unsaturated can come in two different types. You might see the words monounsaturated. That word mono means a single again, so it means that in that long chain molecule you've just got one double carbon-carbon bond. Or you could have polyunsaturated, where you would have multiple double carbon-carbon bonds in that long chain molecule. Okay, so poly means that you would have many carbon-carbon bonds in the molecule, whereas mono means that you'd only have one. So you might see those words used in these kind of questions about oils. Now, we use oils for cooking, like vegetable oils and oils that we fry in and oils that we would cook potatoes in, for example. So there's a few ways we could cook potatoes. We could cook them in water and we could boil them, or we could cook them in a load of oil, which would end up frying them. Oil has more energy than water. Therefore, if we cook food in oil, we're going to take in more energy, and therefore they're less healthy for us than we cook them in water. But cooking in oil also means that oil has a higher boiling point, so we can cook at higher temperatures, and also our food would cook faster. For example, if our boiling point of this oil that we're using is 270 degrees, for example, that is a lot higher than the boiling point of water, which is 100 degrees C. So if we were to use oil to cook our food, it would cook at higher temperatures, and also it would cook faster as well. Now, sometimes they ask you about, for example, a potato and how that would be different if it was cooked in oil or water. And all they want for that is general knowledge-y things. So a potato cooked in oil would be crispier, it would have a different flavour, and it would have a different colour as well. It would also have more energy because the oil contains more energy, and therefore it would be worse for you and less healthy for you than if it's cooked in water. So oils tend to be, unsaturated oils tend to be liquids at room temperature, and they're used for cooking a lot of the time. But there is a process that we can do to make those liquid oils into solid oils over here. So turning from a liquid to solid, and this process is called hydrogenation, and this bit is for the higher tier. So hydrogenation, as the name suggests, you can get a clue from this. Hydrogen. This process is all about adding hydrogen to your oil. For example, if we took an alkene as an example, ethene, we can add hydrogen to that because we said there's room for hydrogen, but the reason why there's not any there is because of that double bond. But what hydrogenation does is add hydrogen by breaking that double bond and then you can fit more hydrogen around it. Now, this process of hydrogenation has very specific conditions, and that is a temperature of 60 degrees and a nickel catalyst. Now, I said before you didn't need to name the catalyst for the other reactions like polymerization and cracking, but you do need to know that the catalyst we're using is a nickel catalyst for the hydrogenation process. And this turns liquid oils into things that are solid at room temperature, like margarine, for example. One thing that you might see in the exam is the word trans fat. They won't ask you about this, but they might use it in a question. So just to bear in mind that a trans fat is a fat that's been just partially hydrogenated. Okay, so these partially hydrogenated fats won't have completely full hydrogen all around them. But clues in the name there, hydrogenation, adding hydrogen, and they're turning into these solid oils rather than the liquid ones from before. Now, these saturated fats, the final little thing, these saturated fats tend to be solid and they are less healthy, and because they increase cholesterol, which clogs up your arteries and leads to things like high blood pressure and heart disease and things like that. Okay, so that's a summary of plant oils. I've got some questions for you to answer just now. So have a go at these and then I'll come back and see if you got them correct. It says, which are healthier, unsaturated or saturated? It's the unsaturated that are healthier. If you add bromine water to an unsaturated oil, what would happen? Well, if you remember, unsaturated oils have double bonds in them. So if you add bromine water, the water will turn from orange to colourless. Third question, what conditions are needed for the hydrogenation process? You need 60 degrees C, 1 mark, and a nickel catalyst for the second mark. The final question says, what are the main steps involved in extracting plant oils for 4 marks? You've got crushing, and then pressing, and then you can have filtering, and you may need that final step of distillation if you need to purify that oil as well after that process. So very well done for those. We're now going to move on to emulsions. Now, normally, if you stick an oil and water together, they will not mix. They will separate like this, where you'll have a suspension of the oil in water. Whereby the opposite thing is an emulsion, okay, when you actually have a mix of oil and water. And the whole reason you have an emulsion is because you have a special molecule called an emulsifier, which allows these two things to mix. So we need to recognise this word in our exam, emulsifier. And that is the molecule that allows oil and water to mix. And these are examples of emulsions. So if you added that emulsifier, they would be able to mix together. And examples include ice creams, mayonnaise, and things like paint, and also beauty products as well, like moisturizers and things like that as well. So these are examples of emulsions, and you might need to give one of those examples as well. So you have a few in mind: ice creams, mayonnaise, paint, moisturizers and things. You need to remember the name of this molecule that is used to make the emulsions. And you also need to remember the advantages of having an emulsion. And those are that they give a better texture, and they give a better coating, and they are thicker. Okay, so oil and water in their own, if you imagine, they're actually quite thin, but if you add that emulsifier, it ends up with a thick substance, and this gives things with properties of a better texture and better coating overall. So a few more things that we need to know for higher. For foundation, as I said, we need to name them, remember the advantages of making an emulsion, and also remember this word emulsifier. For higher tier, we need to go into a little bit more detail. So for higher tier, when we're talking about emulsions, we need to know more about this emulsifier molecule. And this emulsifier molecule that allows the oil and water to mix has two different ends to it. It has a head end and a tail end. Now the head end is what we call hydrophilic. Hydrophilic, it is water loving. Whereas the tail end is hydrophobic or water hating. And this is how the emulsifier works to make an emulsion. Because, for example, if we had a circle to show water and a circle to show oil, we can see what's happening in the two scenarios. So if this here was an oil droplet and this here was water, we would show what's happened. Let's start off with water first of all, and you need to be able to draw these examples in an exam. So if we've got the emulsifier, if it's got the head end, that's hydrophilic, it's water loving, but the tail end is hydrophobic, water hating. So for the water loving, we would have the head end inside the water droplet and the tail end out, because the head end loves water, but the tail end doesn't. And you'd have emulsifier molecules going all around like this. Okay, and I'm not going to draw them all on, but you get the idea. Now the opposite will happen in a droplet of oil. In a droplet of oil, you would get the tail end inside, because that is water hating, and you would get the head end outside. So you need to remember which end of these emulsifiers is water hating, which end is water loving, and remember these terms hydrophobic and hydrophilic. Sometimes there's a silly way to remember it. If you kind of draw a little hat on this guy and call him Phil, you might remember that this end is hydrophilic because it's got the word Phil in it, and then this end is hydrophobic. So this comes up in the higher tier. It's just the idea that to allow the oil and water to mix, the tail end will dissolve in the oil, and the head end, or the hydrophilic end, dissolves in the water. Okay, so an extra bit of emulsions for the higher tier, and now I've just got a few questions on emulsions for you to have a go at. Okay, so the first question then, don't worry if you haven't finished them, you can always pause it and come back, but it says, what is the name of the molecule that is used to help make an emulsion? That is an emulsifier. Give two advantages of emulsions. You could have the idea that it's got a better texture, or better coating, or perhaps the idea that it's thicker. You could also have the idea that it's longer lasting, because some food products that you have that you put emulsifiers in, they can be longer lasting and have a longer shelf life. Two examples, you could have things like paint, ice cream, moisturizers, mayonnaise and things like that. And for the higher tier question, draw the oil droplets on the right and add 5 emulsifier molecules. You need the head end outside, that's hydrophilic, and the tail end inside, like that. So moving on then to Earth structure, we need to know basic bits of geography about the Earth. We've got the crust here. You need to have an awareness as well that the crust is quite a thin layer. We've also got just inside the crust, we've got the mantle, and that's thicker than the crust. And the mantle is slightly liquidy, so it can flow, and that tends to be like the top bit of the mantle around here that can kind of flow and move around a little bit. And that is due to the fact that this core area, at the moment in this picture, it's separated into the inner core and the outer core, but in your exam they'll probably just have one circle for the middle called the core. And inside the core there are radioactive processes. So there's radioactivity going on inside the core, which will release heat energy. And what that does is it causes convection currents in the mantle, where the mantle kind of, the particles in the mantle are rising up and then going down again. And these come important for later on when we talk about tectonic plates. So in the core, there's the radioactivity. A lot of people forget that bit. And this drives convection currents in the mantle. Might as well discuss it now, I suppose. The idea that these convection currents are what move our tectonic plates. Now, the Earth's crust, not the continents you need to look at, the Earth's crust is actually made up, you can't see them on this map, but they're actually made up into several big chunks called tectonic plates. And these tectonic plates are moving around. Because of these convection currents in the mantle, they make these tectonic plates move. And this is how the continents are starting to drift apart from each other. And along these boundaries where you have these tectonic plates is where you will have a lot of volcanic activity, and you'll also have lots of earthquakes and other extreme weather situations as well along these plate boundaries. Moving on, we're going to talk about plate tectonics, but also someone called Alfred Wegener, and I'm just going to discuss this kind of 6-mark question. I'm going to put it in this scenario. It says, how did Alfred Wegener come up with his theory of continental drift, and why was he disbelieved? For around 6 marks. So this could well be a kind of question they ask in the exam. And Alfred Wegener didn't know about tectonic plates at the time. He had no idea about what we've just discussed. The Earth being, the crust of the Earth, being cracked into these kind of plates, like so. He had no idea about that idea at all. But his work suggested that the continents were moving apart, and he called this theory continental drift. So he didn't know how, he didn't know about the convection currents, he didn't know about tectonic plates, but he did have the idea of continental drift, and that was that the continents were moving apart. And let's look at the evidence that he had first of all. He had 3 main bits of evidence. The first one is that there were the same fossils in the areas that he looked in. He mainly looked at these coastlines here of Africa and South America. So these are the ones that you need to refer to in your exam. Africa and South America. And he said that the same fossils in South America and Africa. He also noticed that there were similar rocks in South America and Africa, just shorten that. And finally, he noticed that the coastlines fitted together like a jigsaw. That's how he believed that actually these continents were once together, and that over time they have drifted apart, and this is what he called continental drift. So actually, he suggested that the continents might look a little bit like this, and we know now that they do. And you can see here that South America line joined up to Africa, and that's why, because the animals could pass across here, that's why he'd found similar rocks and similar fossils in the 2 areas. And we know now that to be true because we know about tectonic plates. But at the time, he wasn't believed. And this forms our second part of this question. Why was he disbelieved? Well, there are several reasons. First of all, he was not a geologist. He was an astronomer. So he liked to look into space and look at stars most of the time. So all the hardcore geologists didn't want to believe him. They didn't like him stepping on their turf, okay? Secondly, they came up with an idea that there was a land bridge between the 2 continents. So there was another theory going around at the time. Well, actually, before the sea levels rose here, there was a bridge connecting these 2 continents. And they used that to explain why there were similar fossils, similar rocks in South America and Africa. And a lot of people believed that at the time. So when the new theory came along, they weren't prepared to believe it straight away. And finally, there was no evidence at the time because he didn't know about tectonic plates or convection currents in the mantle. There was no evidence for why the plates would have moved. And he did do a few calculations, but they were wildly inaccurate at the time as to how far the plates were going to move and how fast they were going to move each year. Okay, so bear in mind a 6-marker on Alfred Wegener and tectonic plate theory, because you do have several things that you can write about it. Whenever this is included, it is often 3 or 4 marks anyway, but they could put it into a 6-marker context like that as well. Okay, moving on, we're going to talk about the Earth's early atmosphere and how that evolved over time to the atmosphere that we've got today. So I'm again going to put it in this 6-marker kind of scenario because there's a lot to go through here. We're going to talk about describing how the Earth's atmosphere has evolved over millions of years. So if you've got this kind of question, you need to think about the early atmosphere, how it's changed, and then the modern atmosphere. So let's start off with the early one. There was loads of volcanic activity. There was intense volcanic activity billions of years ago when the Earth first formed. And those volcanoes would have been spewing out things like ammonia, NH3, and water vapour, H2O, and methane, you should know that from the alkanes, CH4, and also loads of carbon dioxide. And actually the early atmosphere had loads of CO2 in it. Now you know now that CO2 and global warming is a problem, and we'll come back to that later, but actually we've only got a tiny amount of CO2 on the Earth now. We've only got about 0.04%, okay, today. But back then, the majority of the atmosphere, we believe, was carbon dioxide. Okay, that's a theory that we have for that early atmosphere billions of years ago. So we're going to go on to now about how this went from a massively CO2 atmosphere to one that is only 0.04% today. And there are several ways in which that happened. First of all, to form the oceans, which didn't exist at the time, water vapour in the air, H2O, condensed. So this caused a change in the atmosphere when the water vapour condensed to form oceans. Then we started to get, several millions and billions of years later, we started to get plants forming. And these plants took in CO2. So we had algae and plants, and marine plants as well, taking in CO2. And they use this for photosynthesis, remember. So algae and plants, as they started to evolve, they were taking away carbon dioxide from the atmosphere. And that was causing the carbon dioxide levels to decrease. Also, the carbon dioxide dissolved in the oceans. And here it got locked up in marine organisms that had calcium carbonate shells. So a lot of the marine organisms at the time, the early kind of ones, not the soft-bodied ones, but after that, they would have had calcium carbonate shells. So the CO2 was locked up in the calcium carbonate shells of marine organisms. You can see that word carbon in there, and carbon is linking into the CO2. So the CO2 is locked up in these shells of marine organisms. And then over millions of years, that would also have got locked up in fossil fuels way under the ground. So the CO2 also was locked up in fossil fuels. And finally, it was also locked up in sedimentary rock as well. So as these marine organisms and other bits of debris were falling down to the bottom of the sea, they'd form that layered sedimentary rock, which was also locking up that CO2. So we're going to go from an area where we have got loads of carbon dioxide in the atmosphere to an atmosphere with very little carbon dioxide because of all of these reasons. So you can see why it could turn into a 6-mark or at least a 7-mark question. And then we get more to the atmosphere that we've got today. And that atmosphere is one with where the majority of it is nitrogen. We've got some oxygen, about 20% of oxygen, and about 1% other gases, which include things like argon and carbon dioxide and water vapour. And this carbon dioxide is actually only at 0.04%. But nevertheless, this 0.04% is slowly increasing. We know this phenomenon is called global warming, whereby the carbon dioxide content is increasing in the atmosphere, causing the Earth's temperatures to increase. Now, one other problem that's happening with this CO2 increasing is that we said before, it gets dissolved in the oceans, and that CO2 being dissolved in the oceans is bad for marine life, bad for marine organisms, because the CO2 dissolving in the water causes acidification, and we call this ocean acidification. So that's an extra problem going on with CO2. But just going back to where we linked from, we started the early atmosphere with the ammonia, the methane, the carbon dioxide and the water vapour getting spewed out those volcanoes, and then gradually the carbon dioxide levels went right down due to the plants being evolved and getting locked up in the oceans and things like that. And now we're in an atmosphere like this, like we have today. And you need to remember the approximate percentages that are of the gases in our atmosphere today. And obviously this O2 was produced when the plants were releasing O2, oxygen, in that photosynthesis process. So here is a summary then of the things that were going on to help you answer that 6-mark question. So the theory of how life formed, well, first of all, there are many theories, not just one. There are many theories, but we only need to focus on one for the exam. Obviously, there are many religious beliefs and religious ideas of how life was formed. And there is this theory of the primordial soup, which we'll discuss now. Now, the primordial soup theory suggests that there were some early gases in the atmosphere, like ones containing nitrogen, like the ammonia, and hydrogen, and CH4, and a bit of nitrogen as well. And all of these gases together, along with a bolt of lightning, formed amino acids. And these amino acids are the building blocks of life. So these go on to make proteins and can make larger molecules and can make much bigger organisms and life forms. Okay, so amino acids are the building blocks of life. And this is the idea that at this time, when all these atmospheric gases were here, there's a lot of lightning activity around as well. And this caused amino acids to be made. And these were kind of collecting then all together, these amino acids, and they started to build on each other and make bigger and bigger and bigger organisms. When they were kind of all together like this in the oceans, they called this the primordial soup. That's where the primordial soup theory comes from. The idea that all these amino acids were collected together in some sort of primordial soup, and then gradually organisms were made from these building blocks. Now, to test that theory then, the idea that you can just get some gases and a spark of lightning and make amino acids, there were scientists called Miller and Urey in the 1950s that tested this idea out. And they had this closed system. You can see there's nothing can go in or out. So you've got a closed system. And it simulated the conditions of the early atmosphere when they believe life formed. So they had some water as the oceans, and that water vapor was then allowed to go up and collect with some other gases like ammonia and methane and hydrogen as well. And what they did, they couldn't obviously have lightning, but they had an electrical spark, and that was to simulate lightning. They liked that question in the exam, why is an electrical spark used? And that was to simulate lightning. And after they did the experiment, they left it for several days, and then when they checked it, they did actually find out that amino acids were formed. So they used this experiment to actually prove the primordial soup theory, in that is how amino acids and life can be formed. So although it doesn't actually prove it to the full extent, because not all of the amino acids in life are formed in their experiment, it does prove that we can have these early gases and that electrical spark can form amino acids. So this is the one theory that we need to remember. It's called primordial soup, and you need to think of all these amino acids collecting together in a water body a little bit like this. Now finally, the fractional distillation of air. And that is for anyone studying the higher tier. And just like we talked about fractional distillation towards the beginning of the video in terms of crude oil, this is about the fractional distillation of air. So again, air is a mixture, like crude oil is a mixture of hydrocarbons. Air is a mixture of different gases, like we've discussed already, including nitrogen, oxygen, and argon, and carbon dioxide, and things like that. And we might want to separate this air into their different gases because they're useful for different processes. So the first thing that we'd have to do is filter the air, and that removes dust and any other particles, solid particles that are in the air. And then we cool it down, and we cool it down to a really low temperature of around -200 degrees C. And then we're going to remove the carbon dioxide, because as we cool this down, the carbon dioxide is a solid when it's cooled down. So the carbon dioxide is a solid, and that's removed as big solid chunk, and the rest of it turns into a liquid. So in the liquid, we've got oxygen, argon, and nitrogen, as well as a few other gases perhaps in there as well. And that then gets put into the fractional distillation column, where it can then be separated into its different gases. Now, the questions on this become a little bit difficult because you need to be thinking about melting point and boiling point of really low temperatures, okay, of negative temperatures. So the liquefied air goes in here once it's cooled down to minus 200 degrees, and the nitrogen comes out the top as a gas, and below we still have liquefied oxygen and argon that comes out of the liquid. So this needs to be separated further in a separate process. So this question says, use the table on the right to answer the questions. Which gases are liquid at minus 200 degrees C? And the way I would recommend to answer these questions is to write down solid to liquid to gas. And here we've got melting and freezing, if it was in the other direction. So melting or freezing in that direction. And in here, this direction, we've got boiling, and in the opposite direction, condensing. So if you remember those changing of states between solids, liquids, and gases, that will help you out for this question. So the first one says, which gases are liquid at minus 200 degrees? Well, if you look at the melting point of helium, that's minus 272, and it boils at minus 269. So the ones that are going to be liquid at minus 200 degrees C are going to be oxygen and nitrogen, because the helium would already have turned into a gas at a much lower temperature, at minus 269 degrees. So the helium would already be a gas. This question says, which gases are solid at minus 250 degrees? Well, that would be oxygen and nitrogen. Because if you look over here, the melting point of helium is much lower, okay? And that's the point where it's going to be melting or freezing and turning from a liquid to a solid. So at minus 272, you'd get the helium turning into a solid. However, at minus 219 and minus 210, this is where you'd get the point it would be turning into a solid. So the gases that are solid at minus 250 would be oxygen and nitrogen. And finally, if the mixture was boiled to minus 190, which gases would be a liquid? Which sounds a bit weird because you're talking about gases and liquids, but they might word it like that in the question. So at minus 190 degrees, the gas that would be a liquid would be oxygen, because it boils at minus 183. And if it boils at minus 183, it is going to turn into a gas.